Okay, this begins our discussion of applications of physics, and we're looking at physics and engineering. And we're going to take the purpose of physics as being to find the quantitative physical laws for the universe. Quantitative is really important because it means that there's numbers behind these laws. And there's many use of this. One is just the understanding of how the universe works, a very, very important part. But also people find that on the basis of understanding these physical laws, they can solve different kinds of problems. And so one application of physics is engineering, where we use these laws to create solutions to hopefully real world problems. And by the way, real world problems may be video games, so they're not necessarily insurmountable or important problems. And so we're going to look at the application of this to some fairly simple engineering problems, and we're going to start off with the design of electronic circuits. In order to make this happen, I'd like to discuss what we're going to do over the next few weeks. This is all project oriented, okay? So you can build stuff and you're going to characterize it and you're going to get it to work, hopefully, and then you're going to characterize, you can actually measure it. And the videos, you'll view these videos at night and take notes in your engineering journal, okay? Because one is I want some indication that you've actually seen these videos. And also you may need these notes for actually completing the projects. And just as importantly, you can use these notes during the final because there will be problems, there will be questions on the final that may deal with these discussions. You're going to design your circuits, and you're going to build and you can test it in class. You can document all this stuff in the journal, and that means that the design, and not only the final design, but the process that led to the design, calculations and the similar things. And then you're going to also go through and have complete test results. You need to characterize these things. You just can't say, wow, it works. You have to say, what does it mean works, and in what considerations. You're going to do all this in the engineering journal, and your engineering journal will have every page sequentially numbered and dated so that you actually have, it's like a real diary. Okay, and then every day that you're going to spend in the lab, it must be witnessed by a colleague, i.e., another student, and they must sign under the statement read and understood so that you have this witnessed. Your journal will be turned in at the end of this section, and it will be graded. Okay, it's going to be worth a couple of labs. So the journal is important. Now, as far as the physical journal, it just needs to be bound paper. Okay, it could be a spiral bound notebook. It could be like a engineering the notebook that you use for your journal in class. If you use the engineering your lab journal, because most of you haven't filled out much in it, that you can start on a new page. Okay, and just basically use that journal. Okay, so you don't have to go out and buy another journal. Okay, so let's talk about an unregulated power supply. We're going to build a power supply, and this is going to be a simple power supply. And what a power supply does, it converts 120 volts AC, alternating current. Okay, that's the stuff that comes out of the wall delivered by PG&E in this location. And we're going to generate approximately 20 volts direct current. And so we're looking at this power supply, and it looks like this. This is a black box view of the power supply. And what happens is that it accepts 120 volts alternating current, okay, out of the wall. And this is actually a plug that fits in the wall. Important safety tip, don't get involved with that plug because 120 volts is dangerous. And it's going to convert that to the right-hand side into a 20 volt DC potential. DC means it's just constant. So if we look at this, is that on this side, we have this alternating current, okay? It's sinusoidal, and it has a period of about 17 milliseconds because it's at 60 hertz. And it has a amplitude, peak to peak, or maximum amplitude of 170 volts. You say, hold it. It says 170 volts here, but only says 120 volts here. And this is this issue of RMS, root mean squared. So what happens is we take, this is the RMS potential, We multiply it by the square root of 2, and we get the maximum potential down here. So this has a peak potential of 170 volts. What we want to do is we want this black box to generate this output. So this is the output from here, and this output is about 20 volts. It's just constant. We want to deliver that 20 volts. It has to have a current behind it to get power. And the easiest way to think about how we generate that is through something that's called a load resistor. Let me see if I can erase this. It's been a while since I've done it. So let's see. Okay, now we can go on to the next one. He said we can go on to the next one. Okay, let's see if I can figure this out. My apologies, it's been a while since I've used this software. Now we got it. Okay, so we're going to break down this problem into a series of problems. And the first step we're going to do is we're going to take this 170 volt RMS, or 170 volt amplitude sinusoid, and we'll convert it to a 20 volt amplitude sinusoid. And the easiest way of doing this is with something that's called a transformer. A transformer is just two coils, so I have a coil over on this side, and I have a coil over this side. This coil is called the primary, and this coil is called the secondary. And the primary is being driven by a potential, and that potential generates a B field or a flux in here. So we have some phi that's being generated through this core. This blue thing is called the core, and then that flux is coupled. It's a mutual inductance is coupled to the secondary coil. So if you have more windings on the primary coil than on the secondary coil, we get a smaller potential. So instead of 170 volts that's out here, we drop it down to 20 volts. And so that's the first step, is to reduce the potential. Let me see if I can figure out how to do this a little faster than the last one. Okay, I did so. Okay, now the next thing we're going to do is we're going to add a diode. Okay, what is a diode? If we talked about them before. A diode conducts only if this side is positive potential with respect to this side. So when this side is positive, we allow the potential through. The diode behaves kind of like a wire. When this is the other way around, which is called reverse bias, okay, it does not conduct, so it's like an open circuit. So what we get out here across the resistor is we just get the positive part of the sinusoid, as shown here. And so here's the positive part of that sinusoid. That's when the diode conducts, and this is what we see out there. So we kind of look like we're getting a 20 volt power supply, but it's got this hoppiness to it. Okay, it's 17 milliseconds. So we need to kind of think about how to get rid of that hoppiness. And the way we get rid of this is this is what a diode does. So we've done that before. Okay, a diode, as I indicated, the diode has a forward bias region where basically it looks like a straight wire. So that's this part. If it has more than 7/10 of volts across it, and then it blocks the rest of it. So we've already seen what a diode does. Okay, so let's add a capacitor. What does a capacitor do? A capacitor stores potential in an electric field, and we have the capacitor right here. So what happens, instead of this thing hopping up and down as we saw before, okay, is that the waveform charges a capacitor right here, and we charge the capacitor here, and we charge the capacitor here, and then the capacitor holds it holds charge and then releases that charge into the resistor. And this is the RC constant right here. So this gets really close to what we wanted for our 20 volt power supply. Matter of fact, it's about as close as we can get. So this is what we're going to do as a very simple power supply, and it approximate our ideal power supply, which is a constant 20 volt power supply. Okay, so this is what it looks like. There's a couple features here that you may be interested in. The first feature is that we have a difference between the sinusoid and the potential on the capacitor. I'm showing by these little green marks as 7/10 of a volt, and that's the forward bias drop on the diode. The other thing is that instead of going flat, that we would have here during the time that the diode is reverse biased is that the capacitor is being discharged by the resistor, which are these lines here. Okay, what is that discharge? That discharge is V max, in this case 20 volts, or 20 volts minus 7/10 of a volt, and then this is the exponential with the RC constant over here. Okay, with time constant RC. And this piece that makes it go back up and down this is called ripple, as you would have the rippling in a pond if you throw a rock into it. And so this ripple operates at about you have the difference between the maximum and the minimum is about 17 milliseconds, which is the period of a 60 hertz sine wave. Now let's get rid of that. Well, let's see if we can make that ripple less. We'll never get rid of it, okay? At least not with this power supply. But we're going to do the following, is that we're going to reduce the ripple by charging the capacitor every half cycle. Now, I'm not going to get into the details of this. You can figure it out by yourself. But what we do is basically, I'm sorry, I think I just did something here, okay? What we do is we will, excuse me, let me undo this. Okay, there we go. Okay, so if this side is positive and this side is negative, what's going to happen is the current is going to flow through this diode, and the current is going to flow through this diode. I'm sorry, the current, I have it backwards, hang on. Let's try this again. So if this side is positive and this side is negative, what's going to happen is we're going to have the current flowing through this way, okay, and the current flowing through this way. Okay, so these two diodes are forward conducting, okay, and so we charge the capacitor. In the other side, okay, when we end up with this side as being negative and this side being positive, which is the negative potential across there, then what we find is that the current flows this way, okay, and also the current flows, it flows to the capacitor, and then the current flows this way. Okay, so what happens is we're charging the capacitor also. So what happens is instead of charging the capacitor every 17 milliseconds, we're charging the capacitor every half of that. And so what happens, we still have ripple, we still have the 7/10 of a volt drop, we still have a decay of the potential across the power supply as shown here, but instead of having the time for the decay as being 17 milliseconds, we half that time. And in considering small ripple, okay, small bouncing up and down, is that we half the ripple by doing that. And so this is called a bridge rectifier. And so it's a handy way of reducing the ripple by about a factor of 2. Okay, the good news is bridge rectifiers are not 4 diodes, they're actually one package. So this one package has 4 pins on it, okay, 4 ways of connecting to it. 2 of the pins, the ones on the left side, we connect the potential to. Let me go through and bring up the pins so we can do it. So this is where the AC goes, right here. And over here, this is where we connect the capacitor in here, over on this side. So we can actually get a bridge rectifier out of this with a single package about as simply as getting a single diode. in this thing. So we'll use a bridge rectifier because the price difference is virtually negligible and the simplicity of using it is just about the same. So we would get rid of this, and then we need to think about one final detail. We're going to build this circuit, okay? But and we're going to use the vernier equipment, so we want to use the differential voltage probe, which we've used before. But the problem with that is it has a maximum range of plus or minus 6 volts. We know that this power supply is going to generate a potential up to 20 volts. So if we just plug the power supply across the digital voltage probe, we'll saturate the digital voltage probe and we won't see much. Okay, so we need to build something that sits in front of the digital voltage probe, and this is called a voltage divider. Okay, so we're going to modify the way we measure this. So let's take a look at it. And so the digital voltage divider, all it does, it's 2 resistors. It's a pretty simple circuit. Okay, and all it does is divide the potential we're trying to test, this V test, through 2 resistors, and we attach our differential voltage probe across this resistor. So the differential voltage probe measures this potential rather than this potential. So if we pick these resistors correctly, we can divide this test. Let me get rid of this. We can divide this test potential by some constant ratio and measure with the probe, and then later on we'll multiply the measurements we're getting on Logger Pro by a number to give us back the true value that we're measuring it. Okay, there's a couple of things we need to do. R1 plus R2 must be large, and R2 must be much smaller than the impedance or the resistance of the digital voltage probe. Okay, which is not an issue because digital voltage probe has about a 10 megohm impedance or resistance. So we have a couple of kind of little constraints there. Okay, so here's a very simple example. We are going to put a R1 is 90K. Let me get rid of this. This is 90K. It's picking up. Okay, 90K ohms, and R2 is only 10K ohms. Windows is fighting me right now, and they generally win when that happens. Hang on. Okay, you'll catch me. There it goes, 10K ohms. And so if we look at the ratio, is that the amount that we present to the sensor, okay, which is this thing I call V probe, and here I call it V sensor, but they're the same thing, okay, is just the test potential, which is over here, okay, divided by this ratio. This is just a voltage divider, and these numbers give us a ratio of about 1/10. So the good news is if we put something, let me do this, is if we put, let's say, 20 volts here, so this is a 20 volt potential, what we get here on the probe is only 2 volts, okay? And that makes the differential voltage probe happy, and this makes Logger Pro happy. So now we're going to end up with some measurement of the Logger Pro that says it's only 2 volts, and then you say, well, it's not only 2 volts because we have to multiply that by 10, so it's indeed actually 20 volts. And so we just need to scale the Logger Pro numbers. Okay, how do we build these things? Building's easy, okay? The big trick is how do we go about calibrating them. In this slide, I show a calibration, example calibration, and all you do is you measure some calibration. That could be a battery, and you get some measurement on that. You pass, then you remeasure that calibration, okay, using the resistive divider. You get another measurement, I call it attenuated measurement, and then you compute the ratio of those two. And then you can then say that for any unknown potential I measure through here, I get some V measure, then I multiply by that ratio to get the true value of the unknown potential. Pretty straightforward thing. Okay, this is what my circuit looks like, and it's not necessarily what your circuit needs to look like. So let's take a look at it. Okay, the first thing we're going to do here is we notice that this is the AC coming in. So right here is AC. And so that means the transformer is out here, and the transformer goes through a special little plug here. Notice that the AC, because the nature of the breadboard, is connected to the little squiggly part of the bridge rectifier. The AC, because of the breadboard, is connected to this little squiggly part. And so we have our two squigglies hooked up. If you hook the AC to the plus or minus side of the rectifier, you'll burn out the rectifier. Don't do that. The negative side of the rectifier goes out here through this wire, and this wire need not be so long, but it is. And that wire is actually connected, and I'll go around here, to the blue side of the breadboard. Generally, the blue side is ground, so we will call this, by convention, we'll say this whole row is ground, and it goes all the way along here. Remember, these are connected all the way along here. The plus side goes to the capacitor, so we run down here, and the plus side goes to the capacitor, which is sitting right here. Okay, so and remember, this is the plus side of the capacitor, and the other side's the negative side of the capacitor. If you plug the capacitor in backwards, you burn it out. Okay, so make sure you understand how to plug this capacitor in. So now we go over here. This is a little resistor, okay, and this resistor goes over here, and it goes to a light emitting diode. And the light emitting diode, when it's plugged in correctly, okay, and of course the other side of the light emitting diode is ground, the light emitting diode of light as it shows here. Okay, so this tells us that the power supply is on. This resistor is very, very important. Okay, so, and you need to set this resistor to the right value, and the value is actually indicated in a little note that I prepared. So this is the light emitting diode that's basically lighting up here. So this is how you can set this up. Let's talk about how we're going to measure these things. And the measurements they're showing here is that basically we want to make sure you have the calibrated attenuator or the divider, so we can use the differential voltage probe. So we've already talked about that. Okay, now this is really important. The transformer can supply only 1 amp. Okay, and so that means that I would like you to limit your load resistor to 40 ohms, and 40 ohms is 1/2 of an amp. Okay, so which is generally a factor of 2. We want a factor of 2 safety margin between the maximum capacity of the transformer and the ability and the maximum current we're pulling out of the transformer. Okay, now the problem with a 40 ohm load resistor, okay, is it's going to dissipate 10 watts, and 10 watts is a lot. So if you use the little tiny resistors that we've used before, those 1/4 watt resistors, what we're going to find is that we'll burn them out. Okay, so I have some special resistors. Some of them are 2 watts and some of them are 10 watts. Use these resistors to load your power supply. By the way, you can find useful stuff without going to 10 to a 1/2 an amp. So you don't necessarily have to use a resistor that's as small as 40 ohms. And so then I'm going to ask you to generate graphs of the output voltage, which is basically the ripple, okay, as a function of time. So that's ripple as a function of time for various, and this is the proper term, responsible loads. Pick the resistors appropriately and use them for short periods of time. There's no reason to make a heater out of this. Compared to the ripple that was predicted by the RC time constant. So do a little bit of math here and clearly record your experiment in your notebook. That means your designs, everything else, and also your results. And the details should be so that another student can replicate your results. And so that's the end of this video. I hope it will help.